So in this part, students, we are going to deal with the thermal conductivity. We will see how this property of a material manifests in the transfer of heat and how it helps us to identify what will be the rate of heat losses, the rate of heat transfers, and then we will go on to define a new term called the thermal resistance. And using this concept, we are going to find out a similarity with electric currents, which we will be using in the further concepts in solving the questions. Let's start thermal conductivity and thermal resistance. Let's see what actually is thermal conductivity and what is the relation that we have for thermal conductivity. Now, thermal conductivity is a parameter that has been defined to measure the conduction of heat through the term of the rate of flow. Now, how is it defined? It's defined in terms of Fourier's law, which says that the heat flux is, let me explain this heat flux. It is the heat flow per unit area and per unit time. Anytime, anywhere, if you find flux, what it actually means is that it's the flow of that thing per unit area per unit time divided by area and time, both of these two. So you always have to keep in mind, flux is always per unit area per unit time. Okay, now so this Q is, I can write it like this, dQ by area into dt. Okay, so this is what this Q actually is. Now this dt by dx, what is this? This is temperature gradient. Means suppose we have a length like this, this length is x, or let's make this length there. Consider at a distance x. Suppose here the temperature is T. At a length x plus dx, this becomes, temperature becomes T plus dt, right? So what is the temperature change in length dx? It is dt. So the gradient will be dt by dx. This is what this term means, that if you move a distance dx, what is the change in temperature dt? That will give you dt by dx. And this k is a constant, which is actually the thermal conductivity with the unit joule per meter per Kelvin per second. This is thermal conductivity. Now if you see here, this is a index 1, we have index 2. This is at a temperature T1, this is temperature T2. Now it is given to you here is that T2 is greater than T1. That means this is the hot end, this is the cold one. So what will happen? The heat will flow from this side to this side. So this shows you the direction of the heat flow, the heat flux. Now this heat flow will depend on this, that is the constant K, which is the property of this material. Whatever the material is, be it of aluminium, steel or iron or steel, whatever, the K value will be different from all of those medium, and so that will be K into dt by dx. What is the change in temperature per unit length? Atomic perspective, we have seen it earlier, that atomic vibrations and free electrons in the hotter region, they transport energy to the cooler regions through oscillations of the molecule. Now let's see here. The ability of the material to conduct heat is measured by thermal conductivity. Means what is the ability? How much, how fast it can conduct, how good it can conduct heat, that is measured by thermal conductivity. If you remember the formula, what is this? Minus K dt by dx. Right? So if this K is greater, which is the thermal conductivity, this Q value would be greater. That means higher thermal conductivity, which is K, means higher or better heat flow. So this is a measure of this. Now why this minus sign is there? Minus sign is because if you see, if you increase the length means if you go to x plus dx, and if this is the hot end, this is the cold end, if you increase the length dx, the temperature actually decreases, right? If you move from here to here, because this is the hot end, this is the cold end, so if you move further apart towards the colder ends, so when x increases, temperature decreases. Now So to make this quantity q positive, because we want to measure a positive value, what we do is that we always put this minus sign. That means this will give you a minus sign, because this is always dt by dx is always negative. So if I multiply this by minus sign, the whole thing will always give me a positive value. So I want q positive, so I put a minus sign here. I hope this is clear. Now in a steady state, now it's important that we first understand what is this steady state. In a steady state, the heat current is proportional to the area of cross section A, proportional to the temperature difference T1 minus T2 between the ends, and inversely proportional to the length x. Now this whole thing that is written is actually this expression, this Fourier's law. We'll see how. Q was minus k dt by dx, right? I told you what is Q. It is the heat flux. Flux means delta Q by area into delta T. So that means what is delta Q by delta T? Simply take the A to this side. So you have minus K into A. What is dt? dt is the temperature difference. That is T1 minus T2 by dx. What is dx? T1 minus T2 is the temperature change between which length? Length L, whichever is given to you. That is L. Along the length L, the temperature changes from T1 to T2. So this is the expression, where K is the thermal conductivity, A is the area of cross section, and these are temperature differences. Let me draw very simple. Now suppose this is a cuboidal connection. Now this face that you see, this face is at a temperature T1. Okay, then this face is at a temperature T2, and I assume that T1 is greater than T2, means this is the hot end, this is the cold end. Now this is T1, this is T2, the thermal conductivity is given to you. So that means this length is L. Okay, so the delta Q by delta T through this material in a steady state, which I haven't told you yet, is constant K into A. What is this A? A is this area of cross section, right? A is this area of cross section that I have shaded here. At this point it is the red one, at this point it's a violet one. So this area you have to take. T1 minus T2 is the temperature differences by L. L is the length of this rod. So if you want to find out the heat flow through this rod, this is the expression that will guide you. Now what is this steady state? I told you that this is valid only when it is in a steady state. Now a steady state is a situation when there is no further change in the state of the body. That means the same thing. What is happening here is that at this point, suppose the temperature is T, at this point the temperature is T dash, at this point the temperature is T double dash. When the steady state will be reached, the temperature of all the portions will become constant. Means this will always be T double dash. See, be very clear. I am not telling you that all the temperature will become capital T, because if that happens, there won't be any heat flow, right? For heat flow, you need a temperature difference. What will happen is that every particular place will have a fixed temperature. This will always have T double dash in a steady state. There will be no change in the state. Initially, to begin with, you had this T1 temperature here and T2 here. Heat starts flowing. So what happens? The temperature at different places will change. Now then there will be a state when the heat that enters is equal to the heat that exits. So if you consider at any point, suppose if you consider this cross section, whatever heat is entering is equal to the heat that is leaving. So what does that mean? That means that the temperature of that portion is a constant now, because no heat is being absorbed. Whatever comes goes out. So that means different portions will have a fixed temperature, but those temperatures will be different. Once all those temperatures becomes equal, there won't be any heat flow. So I hope this steady state is clear. And this expression is true only when you have a steady state. Okay. So now this area, now again you have to see, as I told you, A was the area of cross section at that place. Now if this is not uniform, or if the steady state conditions are not reached, the equation can only be applied to a thin layer of material perpendicular to the heat flow. It's because in that thin layer you can assume that this area is a constant and this steady state has been reached, like this. Suppose if you want to apply at this point and this point, you cannot take a particular area. Suppose this is A1 and this is A2, you cannot take A1 or A2. So what you can do is that you can only consider a very small element here. You can consider its area A and consider the temperature here. Suppose it is T plus dt, and apply only to this small element. You can only apply to this differential element. You cannot apply in this case to this whole of the body at once. You can only apply to a small element and then integrate it, because this is valid only when the area is a constant, not when the area is varying, like this case. In this case you will have to consider a differential element and then do the whole process. Quantity dt by dx is called the temperature gradient. Now the minus sign indicates that dt by dx is negative along the direction of the heat flow, which I explained you earlier. Now what will be the unit of thermal conductivity? You can find out from here. What is delta Q by delta T? Is the rate of heat flow. What is that? Power. Power means watt. Okay, its unit is watt. Watt by area. Area is meter square. dt is Kelvin into dx is meter. So meter gets cancelled. So it's watt per meter per Kelvin or degree Celsius. Now, one face of a copper cube of edge 10 centimeter is maintained at 100 degrees Celsius. So let's make a cube. This is a cube. Its edge is 10 centimeter. If the edge is 10 centimeter, what will be the area? It will be 10 into 10 centimeter square, right? Heat is flowing, suppose in any particular direction. I assume that this one is at 100 degrees Celsius and this is at 0 degrees Celsius, right? So heat will flow from this to this, okay? Now all the other surfaces are covered with an insulating material. It's given that this one, all the other surfaces, they are covered with insulating material. So what that means is that heat cannot go out from this side or this side or this side, from none of the sides. Heat will only enter this side and exit this side. That's the only way of possibility. That means only conduction will happen in this direction. Okay. Find the amount of heat flowing per second through the cube. What is the heat that will flow per second through the cube? Apply the formula. Okay. What is K? Conductivity. 385. Right? What is the area? 10 into 10. Okay. What is delta T? Is 100. By delta X is 10. Now this is in centimeter. So if you convert this to meter, this will become 10 to the power minus 2. This will become 10 to the power minus 4. Right? This 1, 2, 3, 4, 4 zeros will make this 1. Right? This 10 will make this 10 to the power minus 1. When it goes above, it becomes 10. 3850 watt. So this is the rate of heat flow through this cube. So you can see how I have applied this formula. It's a very simple formula and the only formula that is available for conductivity of heat. You can apply this, but only thing that you have to keep in mind is that this is valid only when the area is a constant. It's not valid when the area is changing. That's what you have to keep in mind. Although in the questions you may have a variable k, you may have delta t by delta x as a function of something. All those things can happen. Like suppose it is given that k is alpha t, it depends on temperature, something like that. So you put this expression, in that case you integrate it and then you solve the question. Okay, but the basic formula is the same, the Fourier's law. Okay, so this is the correct one, 3850 watt. So in this part we have talked about what is this thermal conductivity and how this is used to understand what is the heat transfer through material mediums. Now in the next part we are going to talk about this in the form of series and parallel combinations, and we'll see how this similarity with the electric current is being used also in the series and parallel combinations. So stay tuned to Ask IITians for more on this.